Okay, so in today's class, I'm going to start with a simple question that if we have a robot and that robot is supporting a payload, or for that matter, self-weight. Clearly, as you can see, when you have a robot needs to maintain its position and orientation even in static loads. So even the load is static, like a self-weight. If you have the weight of the end effector, to maintain that particular orientation and position, you would have to provide some non-zero torque values at joints. Now, this is super important to understand from roboticist point of view. Even though robot is performing a pick and place operation, or even if the robot is supporting an external load, you are not actually applying forces anywhere else. What you have control over is the joint torques. So the key question here, the practical question here, is if you have a robot arm and that robot arm, say you want to lift it and then hold it at certain position. If you want to lift the robot arm and hold it at certain position, what is the holding torque of the joint motor that will keep that robot arm in that static condition? Now, the next natural extension of this problem is, imagine now you are looking at not the static position, but the dynamic motion of the robot arm. What should be the joint torque trajectory that will take that robot from point A to point B? So in today's class, the first problem that I'm going to solve is, how do we hold that robot arm in a static position? So what, it's very simple. For an example, if I want, this is my robot arm. If I want my robot arm to be at this location, I need to apply some joint torques. Otherwise, the robot arm will not stay there. It will just come down under the weight of its own weight, or under the gravitational force. So how do I maintain a particular orientation and position of the robot arm in static condition? So that would be the first question before we move on to the dynamics of the robot arm. And from next class onwards, we will talk about how do I program the joints so that the robot can go from point A to point B. So the question here is, robot has reached point B and I want that robot to stay at that point. So that is the question that I'm going to solve. And this is also called as the static force analysis. So today's topic, and believe you me that you will see quite a few equations and jugglery, but all this stuff comes from simple equations of statics. So in today's class, we are going to do static force analysis. So static force analysis is answering these fundamental questions. So how to find joint torques that would maintain robots static position. And the second question is, how is it related to Jacobian? So let me take a very simple example. And this is the robot that we have been talking about for a long time. So we have an R robot, and on this R robot, you have an end effector, and there is some weight. Okay, there is some weight on this end effector. So what I'm going to do is, I'm going to look at this robot arm from top view, and I'm going to draw the top view of this robot arm. So even though this robot arm is a three-dimensional robot arm, what I want to do is, I want to draw the top view of this robot arm. So top view of the robot arm comprises of two links. This is link number 1. This is link number 2. And here there is a motor M1. Here there is another motor M2. So motor M1 is providing torque tau 1. Motor M2 is providing torque tau 2. This angle, the angle made by the first link, I'm going to call this theta 1. And the angle made by second link, if you look at our sign conventions, the angle made by the second link is with respect to the first link, which is theta 2. And on here, that I have an external force F. And this force could be the weight of the end effector, or this could be some weight of the part. It could be something that robot is carrying. And now what I want to do is, the question here is, given this F, what is the value of torque 1 and torque 2? What is the value of torque 1 and torque 2 that would maintain the robot arm in theta 1 and theta 2 orientation? Everyone understood the problem setup? So you have this robot arm. There is external load acting on the robot arm, and I don't want that robot arm to collapse under that external load. I want this robot arm to resist that external load. And clearly, the robot arm is not moving. So this is a static problem. And if you remember, can someone tell me the conditions of statics? Summation of forces in the x direction is equal to 0. Summation of forces in y direction is equal to 0. Summation of forces in z direction is equal to 0. Summation of moments about x-axis is 0. Summation of moment about y-axis is 0. And summation of moment about z-axis is 0. So let me set up the axes. This is my x-axis. This is my y-axis. And z is coming through the joint. So now if you were to look at this, this is your z. This is your x. And this is your y. And you are looking from top. Now, since I have done a two-dimensional representation, so actually my robot arm is 3 dimension, but I'm looking from top, so the entire robot arm is in one plane. So the conditions of equilibrium are summation of forces in x direction is equal to 0, summation of forces in y direction is equal to 0, and summation of moments about z direction is equal to 0. Do you agree with me? Now, believe it or not, the conditions of static equilibrium are a special case of Newton's law. What that means, the Newton's law is written as summation of forces in x direction is equal to mass times acceleration in the x direction. Summation of forces in y direction is equal to mass times acceleration in y direction and summation of moment about z direction. And you have to be extremely careful about this equation because we loosely talk about this equation. But let me tell you, this is like I, which is mass moment of inertia times alpha, which is the angular acceleration. But this equation is valid only at certain locations. So here is the difference. And I want to emphasize this because this is not emphasized when you study statics and dynamics. Summation of forces is equal to mass times acceleration is valid on the entire body. Summation of forces in x direction, y direction, z direction will always be mass, which is the scalar quantity, and the acceleration about that direction. Translational acceleration. Everyone agrees to that? However, the last equation, summation of moment is equal to I times alpha. Probably you have seen this equation in its different form. T is equal to I times alpha. Torque is equal to I times alpha. Torque is a twisting moment, which is a moment, which is a rotation. That equation is valid only at 3 points. And remember this, that equation is not valid everywhere. And those 3 points are as long as the point where you are taking moment has fixed. So basically, it's not moving. Point where you are taking moment is the center of mass of that body. And point where you are taking moment has the velocity which has its cross product with the direction vector is equal to 0. And I will talk about those subtle conditions, but please understand T is equal to I alpha is not a blanket equation that you can apply to any point. Moment is about a point. Okay, moment is about a point. So the last equation is only valid at 3-point location. And we will talk about it in details when we talk about the dynamics. But what I want to emphasize here is at this point, if my accelerations are 0, if my ax is 0, my ay is 0, and my angular acceleration alpha is 0, Newton's laws get converted into equations of static equilibrium. Do you agree with me? Everyone understood this? Now, what is the physical interpretation of this? Imagine if you have a robot arm. Imagine if you have a robot arm and that robot arm is moving very slowly. Case 1. So you have a robot arm and now this robot arm is going from point A to point B. It's going very slowly, so that ax, ay, and alpha are close to 0. What you can do is you can find out, and this is very important, and I'll tell you in the last once that all the derivation is done at the moment of enlightenment, I'll show you what that means. That means you can find out torque at time 1. So torque at 1 second, torque at 2 seconds, torque at 3 seconds, torque at 4 seconds, torque at 5 seconds, torque at 6 seconds, torque at 7 seconds, torque at 8 seconds, as if that robot arm is static at that location. And then just feed that torque trajectory. In other words, feed the motor the torque commands like supply torque this, supply torque this, supply torque this, supply torque this, and your robot will create or track the path that you want to track. Everybody understood this? Yes.
So is it considered to be moving at constant speed?
So basically, it's moving very slowly. No, acceleration is 0. So constant velocity, you will have some velocity terms floating around depending upon how you have formulated the problem. But these equations are valid. The word there is quasi-static. So very slowly. So it could be constant velocity, but if the velocity is at higher speed, then you could have some damping effect or something that will, those terms will pop in into those equations. And so this is one trick. So if you design a robot arm, and if you want to find out what should be the joint trajectories, what people do is they actually perform the static analysis. And I will tell you, once you find the Jacobian, static analysis is super simple. They find the static torque trajectories, initially put those static torque trajectories, and then have that robot go from point A to point B slowly, and then gradually increase the speed and add the correction factors. Now, some of you may ask me, and this is from practical robotics point of view, if I have a sequence of torques, so let me give you, I want to go from point A to point B. So what I'm going to do is I'm going to find out the torque values when the robot is at 1 degree, 2 degree, 3 degree, 4 degree, 5 degree, and so on. And now I have this array of torque values. How do I supply these torque values? These torque values get supplied to the motor by means of the motor controller. And depending upon your controller architecture, whether the controller is analog or whether controller is digital, you can change the torque values or the torque that motor is supplying, and then actually achieve the desired motion from point A to point B. But remember, that motion is very, very slow. Everyone understood this? So this is the first level approximation that you can use if you want to build or design the robot. How many of you are comfortable in drawing free body diagrams? Okay, since some of you are good, some of you are not so good, and some of you are sitting on the fence of good and not good, what I will do is, for this problem, I will draw the free body diagrams. Because if you were to use Newton's laws, you will have to use, or you have to draw the free body diagrams. If you use the Lagrangian equation, no need to worry about the free body diagrams. So if you are not comfortable with free body diagrams, don't worry. This is the first and the last time I will draw the free body diagram. Anyway, so what I want to do is, I'm going to start with, first, we have this force F. This force F is making certain angle, and I'm going to call this angle theta. And this angle theta could be different than theta 1, theta 2, or theta 1 plus theta 2. So just to give you an idea, this is theta 1. So the total angle that link 2 is making is theta 1 plus theta 2. So you have this force F. Now this force F has two components. You have F, and I'm going to call this, let me call this as F cosine theta, and this F sine theta. So what I've done, I've resolved this force into its horizontal component and vertical component. And what I'm going to do is, first link 1 or link 2. Consider link 2. If you consider link 2, I'm going to draw the free body diagram. The word free body diagram means we have to free the body. So as you can see that this body was attached at motor M2, and there on the other side you have a force F cosine theta, you have F sine theta. This angle is theta 1 plus theta 2, and this is the hinge. And I'm going to say on this hinge there is a reaction And this reaction I'm going to call as by, because this is going to be joint B, this is going to be joint A, by and bx. Also, there is this unknown joint reaction, which is the torque, which I'm going to call this as tau 2. Now, whenever you free the body, why do we have to free the body? Once we free the body from a joint, internal forces come into picture. These internal forces are the forces that are acting on the joint. Now, what that means is very, very important. That since I have freed the body, so link 1 and link 2 are separate. So what you have is this is link 1. On link 1, you are gonna have the reaction by, which is going down. You are gonna have reaction bx, and you are gonna have reaction moment tau 2. Are you with me so far? Since you have freed the body from the link, or freed the body from the joint forces will come into existence. Now, please understand, as soon as you connect these two bodies, the bx in the horizontal direction going towards right and going towards left will cancel each other. Yeah.
Do we need to add the mass at the center?
Right now, I have not added the mass because that will make things complicated. It's coming next. So don't worry. So right now, so as you can see that the forces and moments drawn in red would cancel forces and moments or the torques drawn in yellow. What that means, as soon as you combine these two links, these internal forces would cancel each other out and you get your original body. Are you with me so far? Now, what I need to do is, let's look at link number 2. This length is L2. And I'm going to apply conditions of static equilibrium. So summation of forces in the x direction is equal to 0. Summation of forces in the x direction is equal to 0. So 0, any force that is going down is negative. Any force that is going up is positive. Why? Because check this out. My x and my y, these are my positive directions. So 0 is equal to minus f cosine theta plus bx. So this gives me bx is equal to f cosine theta. Summation f of y is equal to 0. So that gives me 0 is equal to minus f sine theta is plus by. That's why I get by is equal to f sine theta. Are you with me so far? And the last but not least is the moment. So what I'm going to do is, this is my point B. So I'm going to take moment, summation of moments about B is equal to 0. So 0 is equal to, check this out. Since bx and by are passing through B, the moment given by bx and by is 0. Do you agree with me? The only moment at joint B is tau 2. Curl your fingers in the direction of moment. Curl your fingers in the direction of moment. And do you agree with me? Thumb is coming towards you. So this is your Z. So which means this moment tau 2 is positive. Do you agree with me? Now look at the moment given by the force F sine theta. F sine theta is the force which is going down. The lever arm, so let me first show you the moment, which is F sine theta multiplied by L2 cosine of theta 1 plus theta 2. Curl your fingers in the direction of the moment. Can you see that the moment given by F sine theta around B is clockwise? Curl your fingers. Thumb is going inside the board. So the moment is negative. Are you with me so far? Same thing, F cosine theta. As you can see about B, F cosine theta, the lever arm is L2 multiplied by sine of theta 2, theta 1, theta 2, and the moment is in the counterclockwise direction. Curl your fingers about the moment. Thumb is pointing towards you, which means that moment is positive. Are you with me so far? So plus F cosine theta L2 sine of theta 1 plus theta 2. Everyone understood this? Okay. Now, next thing, what I want to do is, I want to move on to link number 1 or L1. And L1, I'm going to free from the joint. Can you see that there is this joint? I have freed link 1 from the joint. So now what I need to do is, I need to draw the free body diagram. So I would first show the internal forces. This is A. So I'm going to call this as AY, this as AX, and please pay attention to this problem, because after some time, this simple looking problem immediately will turn into a very complex problem. So please understand each and every step. Each and every step is just application of statics, but making sure that we are using the correct notation and correct signs. And then I'm going to use torque 1. And I'm going to repeat the same exercise. So first, summation of forces, and just to be clear, on this, there will be an AY, there will be an AX, and there will be a tau 1. Are you with me so far? That is everything on the hinge. So since I've separated this link from this hinge is fixed. Since I've separated the link from the hinge, these internal forces came into picture. As soon as I combine these two, these internal forces will cancel each other. Every action has equal and opposite reaction. So that's what. So this is the free body diagram. I'm going to apply the conditions of static equilibrium to link number 1. So summation of forces in x direction is equal to 0. And what forces do I have? I have AX, which is going towards the right hand side. Look at our coordinate frame. So I have plus AX minus BX. This tells me AX is equal to BX. Now, since I know value of BX, which is F cosine theta, I can just substitute this over here. AX is equal to F cosine theta. Summation of forces in the y direction is equal to 0. So 0 is equal to plus AY minus BY, which gives me AY is equal to BY, and that gives me AY is equal to F sine theta. Do you agree with me? Now comes the killer part. Summation of moment about A is equal to 0. And at this point, as you can see, there are quite a few moments. So summation of moment at A is equal to 0. AX and AY, they go through point A. So the moment given by AX and AY is 0. You agree with me? However, tau 1 still exists. Curl your fingers in the direction of tau 1. Can you see that tau 1 is positive? So plus tau 1. Now, curl your fingers. Let's move forward. Curl your fingers in the direction of tau 2. Can you see that tau 2 is negative? Right? It's going inside. Coming out positive. Going in negative. Everyone understood this? Good. So minus tau 2. Now we have to look at the moment given by by. So you can see by, this distance, since this is theta 1, is L1 cosine theta 1 and is L1 sine theta 1. So if you look at the moment of by about point A, moment of by about point A, it's by multiplied by L1 cosine theta 1. That moment is negative. Are you with me? So minus by multiplied by L1 cosine theta 1. Now let's look at the moment given by Bx about point A. Curl your fingers in the direction of moment. Bx multiplied by L1 sine theta 1 is going in this direction. Curl your fingers, and that moment is positive. Plus Bx L1 sine theta 1. Are you with me so far? So now we got these equations. Now what I'm going to do is, I'm going to try to rewrite these equations in some meaningful form. Okay. So what I want to know, let me pose the problem again. The problem is, I want that robot arm, and let's not lose sight of the problem that I'm trying to solve. I want that robot arm to be in that orientation and that position supporting the external load F. What tau 1 and tau 2 should I apply? Everyone understood the problem that we are trying to solve? The problem that I'm trying to solve is, I'm given the value of theta 1, I'm given value of theta 2, and I'm given value of external load F. And I want to find out what are the motor torques tau 1 and tau 2 I should apply so that the robot arm can hold that external load. Everyone understood this? So I'm not interested at all in AX, BX, AY, BY, and to be honest with you, AX, BX do not exist in my robot arm. They came into existence because I freed the body, right? But at the end of the day, somebody gave me F, somebody gave me theta 1, somebody gave me theta 2, and asked me what is the value of tau 1 and tau 2. Are you with me so far? So what I'm going to do is, I'm going to go back and write the equations for tau 1 and tau 2. So first, it's actually going to look a little bit complicated, but bear with me. So let's look at the equation for tau 2 first. Tau 2 equation comes from this. So let me pose the question here. Question. Given theta 1, theta 2, and F, and clearly theta, what are tau 1 and tau 2? So this is the question that I want to solve. And for that, what I'm going to do is I'm going to look at the equation for tau2. So tau2, which is I'm going to call this equation 3, and I'm going to call this equation 6. Tau2 is equal to f sine theta L2 cosine of theta 1 plus theta 2 minus f cosine theta L2 sine theta 1 plus theta 2. And the second equation, so consider equation 3 and 6. And then what I'm going to do is I'm going to write down this equation. So tau 1 is equal to, I'm going to take tau 1 on one, so plus tau 2 plus by L1 cosine theta 1 minus bx L1 sine theta 1. So what I did, I took from equation 6, I just took tau 1 on one side, and tau 2, by and bx, they had the negative signs. They become I flipped the signs. Now since tau 2 is already known, what I will do is I will substitute the equation for tau 2. So basically I get f sine theta L2 cosine theta 1 plus theta 2, f cosine L2 sine theta 1 plus theta 2. All this equation can go over here. So that after that is done, here is the equation that we are gonna get. So tau 1 is equal to f sine theta L2 cosine theta 1 plus theta 2 minus f cosine theta L2 sine theta 1 plus theta 2. Now still we have these terms by basically this becomes by, we already f sine theta, so f sine theta multiplied by L cosine L1 cosine theta 1 bx, and bx is f cosine theta minus f cosine theta, which is multiplied by L1 sine theta 1. Are you with me so far? So this is equation 6, equation 7, and equation 8. Everyone with me so far? Now what I'm going to do is I'm going to make a very simple substitution. that will actually make this complex looking equation less complex. I'm going to call f cosine theta as fx, and I'm going to call f sine theta as fy. Just for sign convention, I'm going to call f cosine theta as fx, and I'm going to call f sine theta as fy. So this guy is fx, and I want you to look at this jugglery very, very carefully. F cosine theta, no, f cosine theta is fy, right? F cosine theta, fx, and f sine theta. So this is fy. I think that is the mistake, that fy, and this is fx. Actually, I think I should use a different color. So this is fx. Fx. So let's find out where is fx here. This is fx, and this is a very important step. Fx, where there is another, there is fx. There is fy. And then there is fy. Are you with me so far? Did I miss any fx or fy? Now what I'm gonna do is, I'm gonna collect the terms. So how am I gonna collect the terms? I'm gonna collect the terms so that, very important, I'm gonna collect the terms so that I can write equation 7 and equation 8. I can write equation 7 and I can write equation 8 in a matrix vector form. What I mean by that, and let me make it a little bit more interesting. So this is tau 2 and this is tau 1. So I want to write this something like this: tau 1, then tau 2, is equal to this big matrix. Actually, I'm gonna need more space. This big matrix multiplied by, like, I'm just trying to look for the right colors. So I'm gonna have, actually, let me do it like this. This just for the same convention. I'm gonna say this is tau 1. I'm gonna say tau 2, and then this will be fx, and this will be fy. And now we have to be super smart and super careful to collect the terms. Do you agree with me? So fx is multiplied, and I will underline, fx is multiplying minus L2 sine theta 1 plus theta 2. And let's not forget, there is one more guy, minus L1 sine theta 1. Do you agree with me? Then fy becomes L2 cosine theta 1 plus theta 2. Let's not forget, there is one more guy, L1 cosine theta 1. Do you agree with me? So this guy is my equation 8. Now what I need to do is, I need to go to equation 7. And equation 7 is better than, so minus L2 sine theta 1 plus theta 2. Okay, sine theta 1 plus theta 2, and L2 cosine theta 1 plus theta 2. Do you agree with me? Now let me pose the problem. The problem is, I want my end effector go to a certain orientation where theta 1 and theta 2, f and theta, which means essentially fx is given to me, fy is given to me, theta 1 is given to me, theta 2 is given to me. I need to find out what is the value of tau 1 and tau 2. Do you agree with me? These are the motor torques I need to supply so that that robot arm is in that particular orientation. Everyone agrees? So after doing all this mathematical jugglery, that is what I found. The extension of that is if my robot arm is moving very slowly, very important. If my robot arm is moving very slowly, recognize that my final position is this. And let's assume my f of x and f of y are constant, or they are known at each time step. What I need to do is, if my robot arm initially is horizontal like this, if my robot arm is initially horizontal like this, I want to find out the values of theta 1s and theta 2s at each intermediate step. I want to find out values of theta 1 and theta 2 at each intermediate step and give those torque values. And if I were to do that very slowly, then I know that my robot with the load from this equilibrium position would go to this equilibrium position, would go to this equilibrium position, and finally it will go to that equilibrium position. Do you agree with me? So if I have a pick and place and I want it to go very slowly, I can still use these equations. Are you with me so far? But that is not the point what I want to make. The point I want to make, and this is where the moment of enlightenment comes in. Does anyone remember the equation for Px and Py? So Px is the x position of the end effector. What is the x position of the end effector? X position of the end effector is, can I write down as L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2. The y end effector position is, and we have done this many times, L1 sine theta 1 plus L2 sine theta 1 plus theta 2. Do you agree with me? So I'm going to write that down. And this is super important. So Px is L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2. Py is equal to L1 sine theta 2 plus L2 sine theta 1 plus theta 2. Now what I want to do is, I want to actually find out the change in the Px when my theta changes. So what I want to do is, I want to find out delta Px and I want to find out delta Py. So if I want to find out delta Px and delta Py, so let me pose this problem. I want to find out delta Px, I want to find out delta Py is equal to some matrix multiplied by delta theta 1 and delta theta 2. So let me pose this problem in terms of what we talked about. Can you notice that Px is function of theta 1 and theta 2. Py is function of theta 1 and theta 2. Now what I want to do is, I want to understand how is a teeny tiny change in Px associated with a teeny tiny change in delta theta x and teeny tiny change in theta 2. So in other words, what I want to do is, I want to find out the derivative. So this is how it will go. Delta Px is equal to L1. Derivative of cosine theta becomes sine theta minus sine theta multiplied by delta theta 1 minus, so L2 cosine theta becomes sine theta 1 plus theta 2 delta theta 1 minus L2 sine theta 1 plus theta 2 delta theta 2, just using the chain rule. Everyone with me so far? Everyone understood what I did? I just got the derivative. Delta Py, same thing, L1 cosine theta 2 delta theta 2 plus L2 cosine theta 1 plus theta 2 delta theta 1 plus L2 cosine theta 1 plus theta 2 delta theta 2. And now what I'm going to do is, I'm going to write these equations into this form. Yeah, I can write this equation into this form. So, but only thing is, I'm going to take delta theta 1 outside, delta theta 2 outside, delta theta 1, delta theta 2, delta theta 2. So this is going to look like delta Px, delta Py is equal to, so first minus L1 sine, this is theta 1, sine theta 1 minus L2 sine theta 1 plus theta 2 minus L2 sine theta 1 plus theta 2. Then I get L2 cosine theta 1 plus theta 2. Then I have, and this is the whole thing altogether, this is L2 cosine theta 2 plus L2 cosine theta 1 plus theta 2. And what do I have here? I have delta theta 1 and I have delta theta 2. This is theta 2 by the way, theta 2. Are you with me so far? Does it make sense? Ready for the enlightenment? I want you to look at the matrix that we have derived on top and the matrix what we have derived at bottom. I'll try to make it more dramatic, okay? So, can you see? Can someone tell me the relation, what's, excuse me. What is the difference? So I have L2 cosine theta 1 theta 2. I have L1 sine theta 1 theta 2, L1 cosine theta 1 theta 2, and so on and so forth. So basically, what we have is we have essentially this is the Jacobian. Let me see. Did I do it right? L2, L1 theta 1 plus theta 2 sine theta 1 theta 2. I think here I made a mistake. Yeah, here I made a mistake.
Isn't PY L1 sine theta?
Yeah. So I actually made a mistake here. So I'll write this down. L1 cosine. So because this is theta 1, L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2. And this guy becomes L2 cosine theta 1 plus theta 2. So let me see. Py L1 cosine Py delta Py is L1 cosine L1 cosine. This is cosine theta 1, I think. Made a mistake here. So delta Py cosine theta 1 theta 2 L1 cosine theta 2. So this I made a mistake here. So L1 cosine theta 1 L2 cosine theta 1 theta 2 delta theta 1 L2 cosine theta 1 theta. This is correct. So now you can see that this equation, what you have there is nothing but the transpose of the Jacobian. Yeah. So yeah, I fixed that mistake that I made. So please understand, I don't know if you noticed this. This is L1 sine theta. This is the mistake that I made. And now these equations are correct. Everyone understood this? So what does it mean? It means, remember the forward kinematics analysis that all we did, and at the end we found the Jacobian. As soon as you got the Jacobian, what you can do is you can use that Jacobian to find out the joint torques that are needed to support the static forces. So that's just that one Jacobian. Remember the Jacobian that we derived in last class using MATLAB? That Jacobian would allow you to find out the joint torques that you need for the robots to go from point A to point B. Please understand, this is not magic. This is called as method of virtual work. And unfortunately, method of virtual work is typically the last chapter in your statics class. So probably you have not seen it, but here is the basic idea behind the method of virtual work. So what is method of virtual work? Yeah.
So the diagonal terms of swap in that
Correct, because it's a transpose.
it's transition.
Oh, yeah, it's a transpose of the Jacobian. So, and I will derive this in just a second. So what is work? Work is given as F, force, multiplied by delta X. So force times displacement. If you have torque, what is the work done? Is torque multiplied by the angular displacement. So torque multiplied by angular displacement. So if you look at it, if you have a robot arm, the robot arm that we are trying to solve, and this point is super important, the robot arm that we are trying to solve, we have F multiplied by delta X is equal to tau multiplied by delta theta. Because clearly energy can neither be destroyed nor be created. So energy can only change forms. So on one side, you have the work done by moving the load, and on other side, you have the work done by the motors. So what I'm going to do is, I'm going to do F transpose delta X is equal to tau transpose delta theta. Now, what I'm going to do is, I'm going to write delta X, is equal to Jacobian multiplied by delta theta, because that's what we did. Delta X is equal to Jacobian multiplied by delta theta. So I will write this over here. F transpose is equal to Jacobian delta theta is equal to tau transpose delta theta. Now what I'm going to do is, I'm going to take tau delta theta, which is on the both hand sides, cancel, and now I have F transpose J is equal to tau transpose, and I'm going to take the transpose of both sides. So I'm going to take transpose here, and I'm going to take transpose here. Transpose of a transpose, if you have a matrix A, if you take a transpose, and then if you take a transpose, then you get A. So what that means is, here I have tau. However, if you have a matrix A multiplied by matrix B, and if you are going to do the transpose, then that is B transpose A transpose. So this is going to become J transpose F transpose of transpose. So now what we have here is, we have J transpose F is equal to tau. And now what I want you to do is, tau, this is the equation that we derived, is equal to J transpose F. And this is the same equation that we derived from static force analysis. This guy is same as this. Are you with me so far? So I will repeat. I'll go through this exercise again. And I would strongly encourage you, if you have not understood a part of it, or if you have not followed a part of it, to watch the video lecture or work out this calculation by yourself, because here is what's going to happen. If I were to use Newton's laws, what would change in these equations? Instead of using summation of f of x is equal to 0, summation of f of y is equal to 0, summation of mg is equal to 0, I would use the equations which are on the right hand side. Everyone understood this? And that is where you get your dynamical equations of motion for the robot arm. So you can solve the robot dynamic. So I will repeat the classes this point onwards would involve some complicated math like this. So be prepared. Please try to come to class and work with me on these math problems. So we are trying to solve the static force problems, which means the robot arm is either stationary or moving very slowly, and we want to find out the joint torques that will support the external weight or the self weight. In this particular case, I ignored the self weight of those arms. I say those links are massless. That's why I did not consider the self weight. So I started with a very simple equation of statics. Summation of forces in x direction, y direction are 0. Summation of moment about z is equal to 0. And I got the relationship between the forces and the joint torque too. Since I have drawn the free body diagram, by freeing the joints, internal forces came into existence that gave rise to the equation for link number 1. Then what I did, I tried to simplify these equations by making the substitution f of x and f of y. And I wrote this entire equation as a matrix vector equation. What do I mean by matrix vector equation? Tau 1 is L2 sine this complete this guy multiplied by fx plus this guy multiplied by fy. Tau 2 is L2 this guy multiplied by fx plus this guy multiplied by fy. So that is how I express the equations. And I got this complicated looking expression. But I said, don't worry. Let's find out the position px and py. And as you can see, px and py, we have done this multiple times, is nothing but L1 cosine theta plus L2 cosine theta 1 theta 2. Py is L1 sine theta 1, L2 sine theta 1 theta 2. And what I did, I actually took the derivative. In other words, I wanted to find out the teeny tiny change in px as a function of teeny tiny change in delta theta 1, teeny tiny change in theta 2. So that's why I took the derivative. And then at the end, I wrote this equation like delta px, delta py is equal to 1 matrix of sines and cosines and delta theta 1 and delta theta 2. And lo and behold, what I got is I got Jacobian. And this first equation, this guy is nothing but the transpose of the Jacobian. And this is not magic, but method of virtual work. What is the method of virtual work? Energy can neither be created nor be destroyed. At this point, whatever is work done by the motor, whatever is the work done by the motor is dissipated in the work needed to raise the load. So whatever is the work done by motor, gone in raising the load. So what I have done is I have found out the work done by the load, which is F times delta X is the work done by the load, and work supplied by the motor, which is torque multiplied by delta theta. And then finally, found out the relationship between delta X is equal to Jacobian multiplied by delta theta. Are you with me? And then what I got is, I got taus, which are the motor torques, is equal to transpose of the Jacobian multiplied by the external forces. This is a very powerful concept. And I want you to think about it and master this, because believe it or not, from next class onwards, the things are going to become even more complicated. Any questions on the math that I worked out in this class? Okay, so please come prepared next class and we will actually solve the dynamics problems.